Lecture 7, difference amplifier. So this is going to be a really useful lecture, especially if you ever do work relating to strain gauges and bridge amplifiers. This is a pretty critical one. Looks like my head's getting chopped off. I got a lighting issue in here. All right, let's get into it. Okay, difference amplifier. So you've seen the difference amplifier topology. This is fairly standard. This is sort of one of the original circuits we talk about when we do op-amp analysis. And let me, my head getting chopped off is weirding me out. Maybe I'll just get closer here. So these are extremely important. So, a lot of we kind of present them originally as, oh, you can do subtraction, right? You can, do subtraction, but that's, the main value in difference amplifiers is not, I guess it is technically doing subtraction, but really it's in looking at the difference between two signals. So quite often, our measurement schemes require that we not just look at a signal reference to ground. Quite often we have to look at a signal reference to another signal. And I'd say most of the time when we're dealing with sensitive measurements, that'll be the case. Even if it is a ground, it's usually not going to be a ground that's some perfect, ground signal. It's usually going to be a ground that has some noise on it or something, which also needs to be subtracted out from our signal if they're shared. So doing differential measurements is really important, and there's a lot of particular issues with differential measurements, and we're going to get into some of those today. But a lot of what we do is going to be present some of the issues, present the metrics for some of these issues, and then present sort of the challenge. So we're going to kind of end this lecture today with a problem, we're going to realize we have a big issue that we have to find a way to fix, and then we're going to talk about in the later lectures how to fix that issue. Okay, so first of all, there's a concept of common mode that we need to get out of the way first. So in a normal differential measurement, you're just talking about two input signals, V1 and V2. But as I kind of described just now, a lot of times we're not necessarily looking at two discrete signals and trying to subtract them. A lot of times we're looking at this sort of differential signal. We're looking at a signal that exists as the difference between two signals. And a lot of times those two signals can have a shared signal, which you kind of want to disregard. So for instance, let's say you have a long wire that is measuring the voltage across a solar cell. So it's measuring maybe half of a volt, and it's a very long wire. Let's say it's a kilometer long, just to be ridiculous. And so this really long wire is a kilometer long, and as it travels, it's not one wire, sorry, it's two wires that are touching a solar cell, and those two wires are coming back. And as it travels along, it's making little loops and swoops, and it's traveling around transformers, and it's traveling around, all sorts of other sources of electromagnetic noise. And so as it's coming back to you from this kilometer away solar cell, I'm not quite sure why this is our experimental setup, but as it's coming back to you, its voltages are sort of, both of these wires have picked up a lot of noise. And so they have all this noise, this wiggling on these two signals. But your signal that you care about is that voltage across those two wires. And so a lot of times what we'll do is we sort of look at that, the signal that's shared between two signals, we view that as what's called the common mode. And the common mode is usually not what we're interested in. The common mode, usually we're interested in the difference, which is described as the differential modes. So, and, we can think, there's several ways to think about it. The book makes a big to-do about the equations, but it's fairly straightforward. The differential mode is just the difference between the two signals. And the common mode is just the average of the two signals. So, right, that's just averaging. We're just, so average of the two signals is the common mode, differential mode is the difference. And intuitively what that means is sort of what we just described, that if you have some noise or some carrier or some shared signal between the two that you don't care about, that's the common mode, and it is the difference between them that's what's of interest to you. Okay, so I'm not going to belabor these equations. They're fairly straightforward. Now keep in mind, everything we talk about in this lecture is assuming a balanced it's assuming a balanced difference amplifier. So it's assuming that we have this ratio. The ratio of these resistors is the same as the ratio of these resistors, which is used to produce the gain. Okay, now it's important to note that when we separate signals into common mode and differential mode signals, there's a difference in the perceived input resistance to each of these signals. That might seem strange because you might say to yourself, well, now hold on, there's not actually a voltage supply that's the common mode and two voltage supplies that make these differential modes. That's not actually what's going on. So how can there possibly be two different perceived resistances for these two different signals? And the reason for that is fairly straightforward. The common mode, when you have two signals, I'm going to use my fingers on. Sorry, I banged up my finger here, so I got some green screen on on my fingers here. So when you have two signals, and these two signals are both changing simultaneously, what's happening is the voltage at these inputs is changing simultaneously. So basically, if you are looking at this amplifier and you fix this voltage, so this signal is fixed and this one wiggles up and down, there's going to be a wiggle at this terminal here, right? You're going to have this, you're going to see this, basically this signal pathway sort of pins this voltage. And I mean, I'm exaggerating, of course, here, because if we're looking at ideal case, none of this is true, but basically the two signal pathways are not moving in unison. One is sort of trying to tug away from the other. One is sort of trying to separate itself from the other. The common mode's not that way. The common mode signal is basically both of these inputs are changing simultaneously. They're both traveling up and down. So they do basically see a different resistance in that, one. And this is sort of when we talk about input resistance, often we sort of say this. If you have multiple inputs, assume all the rest of them are fixed, or assume all the rest of them are zero. So normally we're sort of assuming that if there's two signals combining, the other one is staying put, and then we do the input resistance measurement. That would be equivalent to this type of analysis. But that's not what we're dealing with here. Here we're dealing with this case of they're both moving simultaneously. So you get this different behavior, and it's fairly straightforward. Differential input resistance is 2R1, and the common input resistance is going to be the R1 plus R2 divided by 2. Okay. Now, this creates an important issue. We've sort of talked about this circuit as being balanced this whole time, and that's usually our standard assumption, that we have this resistor ratio that is constant for both pathways. And it is that constant resistor ratio, that identical resistor ratio, that results in this cancellation that actually produces the nice clean subtraction. But that's not actually going to be true. So resistors are not perfect. We can't get perfect resistances to get a perfect ratio of resistors, and so we're going to have a mismatch. So we're going to have a resistor error that causes pair imbalance, and it's really important to note what is the impact of this. So basically, how does an error in a resistor value change the overall behavior of the circuit? We skip the lengthy mathematical analysis of this, but we can basically say, so one clean way of representing the gain for a difference amplifier is some differential mode gain, which is here, and some common mode gain here. And now this equation was just, we created this, right? We're just creating these coefficient terms to be descriptive. And if we represent this output of this gain as sort of separating the differential mode and the common mode, we can see the differential mode gain is, the one you recognize, which is R2 over R1, that's sort of the ideal gain. But then you also have this error term, which is created by that resistor imbalance. In this case, this error term epsilon is a fractional resistor error. So for a 1% resistor, a resistor that's off by 1%, this error term would equal 0.01. So mathematically, that's how we're representing this. It's important because sometimes the book does that sort of times 100 nonsense with percentages. So basically this epsilon here would be, for a 1% error, it would be 0.01, just to remind you of that. Okay. So we have a deviation from the ideal in the differential mode. And we also have this, what's almost maybe more important, is this common mode gain. We don't want common mode gain. We want, for an ideal difference amplifier, there is no amplification of the common mode at all. And when we say amplification of the common mode, the royal we, What we mean is, again, that if both signals go up and down the same, right? If both signals are fluctuating the same, the output should be fixed. The output should, we should only be amplifying the difference between the signals. We shouldn't be amplifying the commonality. And which is why seeing the common mode in the output is bad. It's always bad. It's not ideal. And so right now, we get this common mode gain, which is R2 over R1 plus R2 times this error term, this is unfortunate because this basically means that our common mode gain is going to be proportional to our resistor error, which that's a lot, right? We're not talking about, this is not like a 1/1,000,000th of the common mode shows up. This is like 1% of the common mode. So this, as a result of resistor imbalance. So this is a big issue, and this is a big issue that we develop ways to sort of work around in this class. So sometimes it's a lot easier to think about common mode in terms of how much of the common mode goes away versus the differential mode. So a lot of times with a differential amplifier, we like to know, it's easier to represent, if you just say, okay, the differential gain is 0.05, well, that's not necessarily what we care about. What we care about is how much is the differential gain rejected compared to, how much is the common mode rejected compared to the differential mode. And so, for instance, if you have a gain of 1,000,000 amplifier, well, even if your common mode shows up completely perfectly unadjusted, right? Even if you have a gain of 1 for the common mode, if your differential mode gain is 1,000,000, that might be okay because the signal you're looking for is getting amplified 1,000,000 times greater than the common mode, and so maybe that'll work out okay for you. But we create this concept of this common mode rejection ratio. So a rejection ratio is something where the bigger number is better, right? So basically, we're looking at the common mode gain. We're looking at sort of the inverse of the common mode gain and calling that a rejection ratio. So you can see that's the common mode gain is in the denominator here. So it's basically this ratio of the differential mode divided by the common mode, and it's just done in a log scale. It's a log 20 scale, though. That's important to remember. So log 20 versus log 10 is is typically what differentiates power measurements from voltage or current measurements. Okay, so and a good estimate, if we're talking, and this is only when we're talking about the difference amplifier, a good estimate, a close approximation of this is that the common mode rejection ratio is going to be 1 plus the gain, the ratio of resistors for the differential amplifier, divided by the error term, epsilon. So numerically, what does this mean, right? If we have it's a log scale, so a common mode rejection ratio of like 100, we're talking about a 5 times ratio between the, a 10 to the 5 times ratio difference between the differential mode and the common mode gain. Okay. So we've gone through, actually this lecture's gone really quick. So maybe we'll have a short one now. Maybe I'm just in a hurry. I got a meeting coming up after this. So maybe I'm just trying to work my way through this quickly. Maybe I missed stuff, but let's do an example. So one of the common uses of differential amplifiers is to amplify strain gauges. So or gauge bridge networks, basically. So bridge networks are a common tool that are used, and I think you've probably heard of these. We've probably talked about them. They're typically used when your signal arrives in the form of a resistance. So a lot of times a signal, a transducer, something that's pulling a signal from the real world, does so in the form of resistance. There's a lot of strain gauges do this, where basically it's a material when the material gets stretched, the resistance of it changes. There's a lot of chemical sensors that work this way. So basically this chemical sensor is a resistive material that absorbs a certain molecule at a certain temperature, and when it absorbs the molecule, the material sort of inflates, it sort of squishes, sort of dissolves the molecule inside of it and causes it to sort of grow. And that can change the resistance of the material. So there's a lot of times where your physical sensing mechanism is in the form of a resistance. Also, you know, things like photoresistors tend to do this too. But the idea is, if your signal comes in the form of a resistance, well, there's a lot of easy ways to measure resistance, right? You can just apply a voltage to a resistor and measure the current. Easy enough. The challenge is that if you do it that way, any noise on your voltage supply is going to show up in your signal, which can sometimes be huge. So a voltage, it's very common for voltage supplies to have 1% noise. That would be considered a fairly low noise voltage supply, actually 1% noise. So I mean, usually, you know, 5-volt supply, like a USB, the USB standard, I believe, is for a 5-volt supply is 100 millivolts of ripple. So 5 volts, 100 millivolts, that's 1/50th. So 1/50th of your supply signal is noise, which would mean if you're measuring resistance using a voltage like that, you're automatically getting 2% noise. You're automatically getting 2% noise. And a good way to clean this up is with a bridge. So a bridge circuit, essentially you have two sides of the bridge, which are voltage dividers. And so your ratio of resistors, basically the ratio of this resistor to this resistor versus this resistor to this resistor, creates this differential voltage at the sort of the middle of the bridge. And the nice thing about that is that differential voltage highly rejects any noise that comes from your reference voltage here. So basically this differential, you know, by looking at the difference in a balanced ratio of resistors, this differential signal is basically a way to eliminate supply noise. The challenge is you're dealing now with a differential signal. So you have to be able to measure this differential signal. And it also should be noted that this differential signal is going up and down with the noise from the supply. So the common mode of this differential signal, the common mode is proportional to the supply noise. So you really want to get rid of that common mode noise. If you don't get rid of that common mode noise, you're basically not getting rid of your supply noise, or not as much getting rid of your supply noise. So this is a common application, a common need for this sort of a technique or technology. So we have a problem here. So we're saying we need to build a differential amplifier with a gain of 100. That's fairly common. A lot of times these bridge amplifiers will be gain of 1,000 or 10,000. It's not uncommon. So we need a gain of 100. We assume we're using a standard difference amplifier topology. What resistor tolerance is necessary to ensure a common mode rejection ratio of greater than 100 dB. Okay. Well, let's go back to our main circuit here, right? We have a, so with the difference amplifier, differential mode gain, you know, ignoring this for right now, we don't have to worry about that too much right now, but the differential mode gain is the ratio R2 over R1. So basically for this circuit, we have R2 over R1 is going to have to equal 100 because we're doing a gain of 100 measurement. Okay, so now let's go back to the CMMR equation. Oops. So using this CMMR equation, we have 1 plus this ratio of resistors divided by the error times 20 log 10. So we can start to produce. So we need a CMMR has to be greater than 100. So let's just solve for CMMR equals 100. So we have 100 equals 20 log 10 of 1 plus R2 over R1. So it's going to be 1 plus 100 divided by this error term. All right, so basically this is going to be 10 to the 5 equals 1 plus 1. Oh. 10 to the 5 equals 101 divided by the error term here. So the error term so our resistor error has to be less than 0.00101. So basically, our resistor, this is about equal to a 0.1% resistor. So 0.1% accurate resistors are very expensive. You can buy these. You can absolutely shop for these on DigiKey. These are going to be very expensive. Not only are these going to be kind of expensive, but you have to worry about how stable they are, right? Does their resistance change over time? Does it change with temperature? If the only room you have is 0.1% error in a resistor value, you're in real trouble. It's going to be very difficult to avoid this kind of, it's not difficult. Sorry, I shouldn't say that. It's going to be expensive. It's going to be expensive to guarantee this. And maybe that's okay. Maybe that's fine. But if you really want to make sure this is stable for a long time, doesn't need to be recalibrated, you're going to be forking out some money to make this work for 0.1% resistors that are stable over a long period of time. So, and this creates some solutions that we're going to talk about in the next video. So an easy solution is to have a variable resistor. An easy solution is to literally just have a calibration resistor that's built into this system where somebody has to come in and perform actually measure the common mode, and somebody has to turn a little potentiometer until that common mode goes away. And that's fairly common. That's one common solution. There's other more advanced ways as well. So there's special types of amplifiers that you can get that have active ways of sort of correcting their own common mode error, active ways of sort of keeping themselves perfect. I don't know how much we'll get into those, but they do exist. Now, another important thing is with common mode rejection ratio, remember an op-amp itself is a type of differential amplifier. An op-amp itself is a differential amplifier. So an op-amp itself will have a common mode rejection ratio. So we've always assumed, right, that it just takes the difference between these terminals and amplifies it, by alpha, right, by some open loop gain term. But actually, there's also some noise, right? So there's also some common mode noise. So with real op-amps, if you have both input terminal voltages go up and down, you will see some of that show up on the output of the op-amp. So it's an important thing to keep in mind. Common mode error, common mode rejection ratio, very important concept in amplifier design. And it's something we will continue to talk about. And it's something, of all the things, if you work with these op-amps going forward or any amplifier going forward in your future career, common mode rejection ratio is absolutely something you will see come back again and again and again. It's a very important concept. Also, more and more signals are becoming differential signals. So pretty much now all high speed, pretty much all FPGAs, almost all high speed electronics communicate with LVDS, low voltage differential signals. And so, these are high speed differential signals where you have to reject the common mode from these signals because the common mode is easily introduced by noise or all sorts of other things like that. So things like HDMI cables. Now they're not going to use a normal op amp at the end of them. Just so you know, you're not going to be amplifying. Typically, you're not going to be building a resistive op amp circuit to amplify a 3 gigahertz signal. Usually, they have other ways of doing it, but you will be using an amplifier, and common mode rejection becomes an important element of that. So, thank you for watching. I will talk to you. One more important thing I forgot to mention. I'm popping back into a video because I wanted to add one more piece that I forgot about. So one of the cool things about common mode and differential mode gain is it can be very easy to test, both experimentally and in terms of just sort of doing a test voltage for if you're dealing with a circuit that you're trying to analyze. So if you're trying to find the common mode gain or differential mode gain, of course, if you're dealing with the sort of standard circuit topology that we went over in this video, you can just use the equations for that. But if you don't have that, it's a fairly easy thing to test for. So choosing a proper set of test inputs can allow you to very easily directly measure these gains or calculate these gains. So for instance, if we were looking at this amplifier here, I'm just going to pluck in some real values here. So let's just say we have 1K and then 4K and then 1K, and then let's say this is 3.9K or something, right? So just estimate some slightly off kind of thing. I'm not actually going to go all the way through this. I'm just trying to just give you a real world time where you would want to do a calculation like this. So if you were given this circuit and you were told find the differential mode gain and the common mode gain, one easy thing you could just do is you could just say, well, let's just set V2 equals 0 and V1 equals 0 and calculate VO. So in this case, ideal analysis is pretty easy. So when V1, when everything's 0, this output voltage is going to have to be 0. Oops, sorry. And then what we could do is if we're trying to find the for instance, like the differential mode gain, for the differential mode gain, we could just set both of these to 1. So if both of these inputs are now 1 volt, how much differential mode do we have at the input? So we have 1 volt differential at the input. Oh, sorry, not differential, sorry. We have 1 volt common mode, right? So we have 1 volt common and we have 0 differential, right? When both inputs were 0, we had 0 common, 0 differential. When both inputs are 1, we have 1 volt common and 0 volts differential. So if we then calculated this, right, we could go through, we calculate this VP, right? We could find the currents, we could do all of this feedback, find VO. And then if we solve for this with both of our inputs equal to 1, we could simply take this voltage minus 0 divided by 1, which is our change in our common mode voltage, and that would give us our common mode gain. And then if we wanted to do differential mode gain, all we'd have to do is we'd have to pick a set of test inputs where the common mode is 0 and the differential is 1. So how could we do that? This is typically where when students are testing a circuit, this is typically where they make a mistake. So what test inputs would we use to get a common mode of 0 and a differential mode of 1? A lot of times students just do this. They say, oh, do 1 volt here and do 0 volts here. That is indeed a differential mode of 1. But the problem is, what's our common mode for this? Our common mode is going to be 1 plus 0 divided by 2. So the problem is, if we do this 1 volt, 0 volt test on our circuit, that will give us an output value which has some differential mode gain, but it also has some common mode gain. So what should we do if we're trying to directly find the common mode, or sorry, if we're directly trying to find the differential mode gain? Well, one thing we could do is we could do, for instance, 0.5 volts and negative 0.5 volts. This would be a common mode of 0, a differential mode of 1. But if we're doing tests, if we're doing a test, forget that. Like, well, let's just do, let's use ones, right? I don't want to use 0.5s. I don't want to have fractions if I'm just creating values to test. So sometimes we do something like this. Sometimes we just do a 1 and a negative 1. And then we just have to keep in mind that our differential input is 2. So whatever output we get for the voltage, we'd have to divide that by 2 in order to get our differential mode gain. The other thing is, we can just stick with something like this. We can just stick with a 0 and a 1. And if we do this after having already solved for the common mode gain, we can just subtract it back out. So if we do this, so we can always say, go back to our equation. We can always use this. So we can always say V out equals, so in this case, if it was 0 and 1, it would be times 0.5 plus and assuming we had already solved for the common mode, we could then solve for, once we use the 0 and 1, we could calculate our V out, and then we could solve for that differential mode. So it's just, I'm mainly warning people because there is a homework problem that I like to give, which is, it's a little bit later on in a 2-stage cascaded amplifier, where basically you need to calculate the differential mode gain and the common mode gain and find the common mode rejection ratio. And the way to do it is to just do it with test voltages. But I see students make this mistake a lot, where they use a 0 and a 1 volt input to be their 1 volt differential gain, or to do their 1 volt differential test. But they have to keep in mind there's a little bit of common mode there too. So that's okay. If you've already solved for the common mode gain, you can just subtract it out. It'll work out okay. But if you haven't, it's just something to keep in mind. I just wanted to add this because as I was doing the video post-processing, I was like, I forgot to talk about this. So I wanted to just toss it in there. The earlier we mentioned this, the better. It's actually very nice, though. This is also, if you have a physical circuit, this is typically how you will test. You'll basically do this to test the common mode and differential mode gain. You can have a function generator that produces, a 0, 1 volt steps on these inputs. And you can just physically measure, you can look at the output of the oscope. You can see sort of the size of the steps of the waveform that are coming out of it. And, and this works great for that. So this concept of do test voltages works great for common mode and differential mode gain. Okay.